Okay, so today we're going to learn how to read a solubility curve. And remember, we talked on Friday about solubility as in how much can dissolve in a particular amount of solvent. In this case, for this graph, the solvent is water. So let's first understand what's going on here. It says solute per 100 grams of water. Well, the density of water is what the metric system is designed around. Water is like the cornerstone of most of our units, and grams and milliliters are one of them, just like temperature is. It's not just a convenience that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. It's that way for a reason. We made the temperature scale ourselves to make it convenient. So the density of water is 1 gram per milliliter. You're going to see it written like that. That means that 1 gram of H2O has a volume of 1 milliliter. So if I'm in 100 grams of H2O, what is the volume of 100 grams of H2O? So the good thing about the metric system is that we can go back and forth between mass and volume using the density. So I'm going to be dissolving all of my solutes in 100 grams of water as the solvent. So the solubility would be how much of each of these salts is going to dissolve in 100 grams of water. So first, let's kind of look at some of these. We're going to separate these into two different types of lines. Some of the lines, the solubility increases with increasing temperature. Some of the lines, that's not the case. Who can find a line where the solubility decreases as temperature increases? Even NaCl, see how it increases? Not a lot, but it increases a little bit as temperature increases. Now let's highlight all of these that do not increase with increasing temperature. These, the solubility decreases with increasing temperature. So when we're increasing the temperature, if the solubility goes up, that's as one goes up, the other goes up. It's called a direct relationship. Let's list some of our direct relationship. And I want you to take a second and see if you can find a similarity between these substances. We're going to look at these compounds and see if we can find a similarity in the structure there. One's a metal and one's a non-metal. Somebody's got their thinking cap on today. What is it called when you have a metal bonded to a non-metal? What are those types of compounds called? These are ionic. Now, let's look at the other one. Not indirect. The relationship's not indirect. If one goes up and the other goes down, this is called an inverse relationship. I'm going to list the ones that have an inverse relationship, and we're going to see if we can find similarities there. What kind of compounds are these? Those are the covalent ones. But it's not really whether it's ionic or covalent that dictates this. What we're dealing with here is the inverse relationships. The covalent compounds are small covalent compounds and are therefore gases at standard condition. All of these are ionic compounds. They're locked into rigid crystal lattices. So these are all solids at room temperature, unless you're doing what we're doing, which is in dissolving it in water, making aqueous solutions. So it's the differences in structure that cause the differences in solubility. So let's see what that means. I'm going to pick one that has the greatest slope. Just like in math class, the graphs in chemistry class tell you the same thing too. So the one with the greatest slope has the greatest change in solubility with relationship to temperature. So it's the one where the solubility changes at the greatest rate when you increase the temperature. And that's going to be KNO3. I'm going to pick a random temperature here. Let's pick 60 degrees Celsius. So at 60 degrees Celsius, I can dissolve about 108 grams of KNO3 in 100 grams of H2O. This is how we write these relationships. This on the line would be considered a saturated solution. It also represents the solubility. So if I ask you for the solubility at that particular temperature, this is what you would write down. So let's look at this. Anything on this line is going to be considered a saturated solution. But what if you're not on the line? What if I say I have 70 grams of KNO3 dissolved in 100 grams of water? Anything down here is going to be what's called an unsaturated solution. So any of the values underneath the curves are going to be called unsaturated. So if I wanted to describe a solution that has 70 grams dissolved in 100 grams of water, I'm going to call this solution unsaturated, meaning that I could dissolve more. How much more? Well, I have 70 grams in there already. I could dissolve a maximum of 108 grams. I already have 70 grams. So how much more would dissolve? 38 more grams of KNO3 would dissolve in this solution. Anything above this line that has more dissolved in it, now if you're smart, you should be saying, well, you just told me this is the maximum that can be dissolved, right? Here is the maximum. How could I possibly have any more than that? And here's where you got to put some thought into it. Here's how we make a supersaturated solution, because up here, this is going to be called supersaturated. How we do this is I would make a saturated solution or an unsaturated solution. It doesn't matter. I'm going to take this saturated solution, and what I'm going to do is I'm going to heat it up. Let's just raise the temperature 10 degrees, 20 degrees. How about if I heat it up to 80 degrees Celsius? Once I heat it up to 80 degrees Celsius, now I can add more solid in there and it will dissolve. I'm going to add the 140 grams and it's going to be an unsaturated solution right now. I have a solution with 100 grams of water and 140 grams of KNO3 at 80 degrees Celsius. Then I'm going to sit it on the counter and I'm going to let it go. I'm going to let it be. And what will happen is the temperature will start to drop. As long as I do not touch the beaker, it will stay dissolved. If I were to even add, say I accidentally dropped one more crystal of solid in there, it would disrupt the supersaturated solution and a bunch of particles would come out of solution. So this is how you make a supersaturated solution. You might think to yourself, what's the point of that? There's actually a lot of applications of it. If anybody has ever made fudge, anybody have a family that makes fudge at home? If you ever make fudge, you might have heard like how hard it is and how they have recipes like no-fail fudge. And it's just not an easy thing to make because you're dealing with supersaturated solutions. So what happens is you have this supersaturated fudge solution that is like a little bit like tar consistency. But if you accidentally drop a piece of sugar in there, you're going to ruin the whole pan of it. So supersaturated solutions are kind of delicate in that if you disturb them, shake them, touch them, it will disrupt it and a lot will happen. And let's talk about what's going to happen. So picture yourself if you've ever had tea or coffee. If you like it really sweet, you're going to put sugar in it. And have you ever kept adding sugar and it's dissolving? Then at some point in time, it stops dissolving, right? That's because you are at a saturated solution. You can't add more unless you heat it up. So if you were at a saturated solution normally and you add more sugar, what happens to the sugar? Sinks to the bottom and sits there, and it's called a precipitate. If I heated that solution up, then you could dissolve that. And once you let it cool down, you will have a supersaturated solution. I'm going to pick NH4Cl, and I'm going to say, what is the solubility of NH4Cl at 80 degrees? So I'm going to go here. I'm going to say the solubility is like how much does it take to make a saturated solution? And this is a saturated solution for an ionic substance. The reason that ionic substances increase with increasing temperature is because when you heat water up, the particles start moving faster. When the particles start moving faster, they separate from each other a little bit. So if you can think of things vibrating, and the more they're vibrating, the more they're going to have space between them. And that's where the ions go. So that's why ionic substances increase with increasing temperature the faster the molecules go. Because the density of water is 1 gram per milliliter at 4 degrees Celsius. As you get colder than that, the density starts to decrease. As you get warmer than that, the density starts to decrease. And that's because the particles are further apart and there's more room to dissolve. Gases are exactly the opposite. If you have gases dissolved in water and you start to increase the temperature, you might have done this at home. You ever put a pot of water on the stove to boil? It's not boiling, but you see bubbles along the side. The bubbles you see are coming from the fact that you're heating the temperature of the water up and the gas is dissolved and they're also getting heated up and the gas particles are moving faster. They will find each other and they will create what we call a bubble. And then they'll stick to the side because they have to have what's called a site of nucleation, meaning a site where that they can gather together. And that's what you're seeing there. So as you heat gases up, they start to move faster and they will eventually have enough kinetic energy to escape out of solution. So if you are ever curious how or why sometimes you make ice cubes and they come out like white, and sometimes you make ice cubes and they come out clear, If you want the clear ice cubes, if you're doing something fancy, making a fancy drink, you want the clear ice cubes, boil your water first. Because what makes them white is the dissolved gases that are trapped in there as you freeze them. So let's see. I'm going to read this at 80 degrees Celsius. I'm going to say it's not that easy to read. I'm going to say that it's going to dissolve 67 grams of NH4Cl. And then I have to report it like this in 100 grams of water. And the reason we're going to do this is because what if they gave you a problem that said, I don't have 100 grams of water. I have 50 grams of water. And you want to know how much can dissolve in 50 grams of water. Well, just because it's not on the graph doesn't mean that you can't read it. So if 67 dissolves in 100 grams of water, you're going to rearrange this equation and solve for X, and it's going to be 33.5 grams of NH4Cl. So you can also do problems. This is how you would do a ratio. If I tell you to do a ratio, look up this problem. You might want to label it as a ratio problem. The other thing I want to point out, and the reason that I spend so much time on this graph is because I see it on the ACT and the SAT all the time. I did look through the PSAT this year. It wasn't on there, right? There's a higher probability that you'll see this graph on one of your next standardized testing. They love this graph because it's got a lot of things going on, and it takes some graphing skills to show that. So I can look and say, they might ask me a question on a standardized test about how much Ki would dissolve in 50 degrees Celsius water. And you're going to look and say, well, that's not on there. Well, you can do what's called extrapolating a graph, and you can read some things that are off of the graph. You may not be able to read exactly what it is, but you can make some inferences. So they're going to try to trick you into saying, I don't know anything about what happens at 50 degrees Celsius for Ki because it's not on the graph. But you can extrapolate off, and what you can say is that more than 150 grams will dissolve. So there are some things you can say about this that are not on the graph. So remember, we talked about the density of water as 1 gram is equal to 1 milliliter. Another thing that's easy about the metric system, what this gives me, it gives me the ability to change between mass and volume. Now let's talk about the ability to change between distance and volume. This is why the metric system is our friend. English system, not so much. So let's say I have a box that is 1 centimeter on each side. Do we all know the formula for calculating the volume of a cube? So my volume is going to be 1 centimeter times 1 centimeter times 1 centimeter. So I took a ruler out and I measured and I made a box that was 1 centimeter on each side. And the volume of the box is 1 centimeter cubed. Well, we rebranded 1 centimeter cubed as 1 milliliter. So now in the metric system, we have a super easy way to convert between mass, volume, and distance or length. Let's make another box. I'm going to try to make it as close as I can to the size we're looking for. Next, I'm going to make a box that is on each side a decimeter. How these are related is 1 decimeter is 10 centimeters. So they're 1 decimal point away from each other. If I have a box that is 1 decimeter on each side, my volume is 1 decimeter cubed. And we rebranded this as 1 liter. So now let's connect these to each other. If I have 1 liter, which is 1 decimeter cubed, this is what 1 decimeter cubed is. In order to cancel each of these decimeters, I'm going to use this equivalency statement. Oops. That'll give me a chance to cancel all these decimeters out. And I'll get 1 liter is 1,000 centimeters cubed, or 1,000 milliliters. Isn't that a clever trick? Have you ever tried to do that with the English system? You guys think you like the English system, don't you? Do we know how many ounces are in a cup?
16.
Okay. Can you convert that to cubic feet so we can get distance? Can we even convert cubic feet into cubic inches, which is what we'd want to do? Yes.
Why do we have 10 centimeters over every 1 decimeter?
Because there's 10 centimeters in 1 decimeter. This is what I wrote up here. This is, if you looked at a number line, a centimeter is right next to a decimeter. And these prefixes are all to add on to base units like meters in order to make smaller or larger units. It's really brilliant if you think about it, because we did something where we did ounces and cups and pints and gallons and quarts, and none of them are related to each other, and nobody ever remembers the conversion factors. Do you guys know how many ounces there are in a gallon? See, we had like 4 different answers. Were any of them right? There's 128 ounces in a gallon. So we've been using this our entire life and we still don't know it. The reason why is it's hard and it doesn't make any sense, and you simply have to remember it. Too much work. In the decimal system, I could just move the decimal points 1 at a time and I get different size units. And there's never any difficult calculations. Like this, even this, I'd want to pull out my calculator for, right? Can anybody multiply 12 times 12 times 12 in their head? I don't even remember what it is. I'm not going to multiply it in my head. 1,728. I'm going to take your word for it. But let me tell you what is easy. There's 1,000 meters in a kilometer. How many meters are in 2 kilometers? How many meters are in 10 kilometers? Okay. Do we know how many feet are in a mile? 5,280. Not too hard to memorize, though. We can probably come up with 2 miles in our head, can't we? 5,280 times 2. How about 7.5 miles? You'd want to get a calculator out, right? But there's 1,000 meters in a meter. 1,000 meters in a kilometer. How many meters are in 7.5 kilometers? 7,500. We can do that easy. So metric system, our friend, very easy. Other ones are not so easy, other conversions. So the whole point of this is, though, we're going to put this out of our mind here. This is why we don't use this in chemistry class. It's too hard. I want you to recognize that when you see centimeter cubed, it's the same as a milliliter. When you see decimeter cubed, it's the same as a liter. So oddly enough, it's so easy that it can be confusing. So you can simply replace centimeter cubed with milliliter and you're good to go. So 7.5 centimeters cubed is equal to 7.5 milliliters. Replacement. Can't do that with the English system. It's just the metric system.